はい。本日の談話会は、現在東京大学の、客員教授で日仏連携機構の、日仏数学連携機構の、機構長をされている、ペヴナー先生で、タイトルは、Symmetry Baking for Branching Problems と。よろしくお願いします。
はい。どうぞよろしくお願いします。So, thank you very much for the introduction. And so I'm very honored to have this opportunity to give a talk at the Colloquium of the Graduate School of Mathematical Sciences, and I'm very grateful for the invitation. So today I would like to give an overview on a series of very recent results based basically on a joint work with Professor Kobayashi in representation theory of real reductive Lie groups. And the message I would like to convey is that there are many interesting, open and challenging problems and questions in this field. Interesting because they are on the interface between various different branches of mathematics, and also challenging because it's a quite old topic. There are many different ways to enter into this topic. It's kind of huge forest. There are many ways, many paths in this forest, and some of them very large with a lot of traffic, some small paths. And so I would like to insist on this active and open questions. Okay, so let me very briefly recall, with any pretension to completeness, recall some basic problems in representation theory, and then I will emphasize on the concrete results. So by representation, of course, we understand a way to realize given abstract algebraic structure by matrices. So by linear transformations on some vector spaces, in a way that an abstract group law becomes just the usual composition of linear transformations, usual matrix multiplication. And fortunately, there are a lot of such ways to realize groups by linear transformations. And in this theory, which appeared more than 100 years ago, one may, of course, it's a very personal point of view, but today I would like to emphasize maybe two basic questions. So first one, very natural, one is to understand the structure of elementary blocks in the representation theory. By elementary blocks, I mean here irreducible representations. For some reasons, it's meaningful and challenging to understand the structure of unitary reducible representations, and I will say a few words about the description of the set of such objects. But this is, let's say, one, maybe the first basic question to understand the objects that we are dealing with. For instance, if we consider the symmetry group, there's a very beautiful, it has a very interesting, beautiful and rich representation theory. One may realize permutations by linear transformations, not just of a vector space of the same rank as the order of the group, where the group actually acts naturally by permutation of basis vectors, but it has some other non-trivial representations. And it turns out that such irreducible ones, the basic elements, are described or parametrized by partitions of integers, by Young diagrams. Okay? So the techniques are of combinatorial nature. That was understood more or less 100 years ago. And if we go further in a historical line and consider representation theory of compact Lie groups, then there are fundamental results obtained in 30s, 40s, and 50s of the last century. Maybe one may mention the Petrov-Weil theorem, which mixes techniques from harmonic analysis, functional analysis, and explains how to understand the space of square integrable functions on a given compact group in terms of a kind of non-commutative Fourier analysis. And so it says how to decompose a specific representation, a regular representation of a group, into elementary blocks. And another theorem, or more precisely, a series of theorems summarized as a Borel-Weil-Bott theorem, says how these elementary blocks look like. So they are parametrized by some algebraic objects, which are highest weights. They can be realized in some concrete spaces of cohomologies, of Flach varieties. So there's some topological aspects of the theory. And already in this setting, we see the interplay between different and various type of mathematics in some sense. So this week we had a very nice series of lectures by Professor Inoue about the representation theory of nilpotent and solvable regroups. And completely different type of mathematics appeared in this context, and it was developed in end of 60s, beginning of 70s, the last century by Kirillov and Kostant and other experts in this field, which mixes symplectic geometry, representation theory, maybe in some sense mathematical physics as well. So that was maybe motivation. And this idea, this philosophy, as we discussed a few minutes ago, parameterizes irreducible representations by geometrical objects, which are some specific symplectic manifolds attached in a canonical way to the group that we are talking about. Going even further in the direction of expanding the Lie structure, we may wonder what happens with the representation theory of real reductive Lie groups. So the situation becomes more complicated, more involved, in some sense more challenging. There are different techniques, many outstanding results, but even now there's no general understanding of the set of all irreducible unitary representations. I don't talk about other type of representation, but already for the unitary dual, there's no global knowledge for such as in some sense, natural group as symplectic group. So for instance, for the GLN, there was a seminal work of David Vaughan in maybe late 80s, the last century, when he gave the concrete description of the unitary dual of the general linear group, but for symplectic group already the classification is not complete. So this is just to say that it's a very challenging and very, very complicated problems. Okay. Another fact, which is quite important for the sequel, is that if we have a unitary representation of a locally compact group, then we may decompose it into these irreducible pieces, into elementary blocks. And this is the Mautner theorem that goes back to 50s, so it's a fundamental result. And what is important is that if we deal with real reductive Lie groups like GLN, SPN, for instance, then such a decomposition becomes unique. And this is very important if you want to do some further things. And of course, finding such a measure that will parameterize the set of non-trivial ingredients, count the multiplicities, are very highly non-trivial questions. And the best situation is where every ingredient appears at most once, then really we may give some sense to such a decomposition, identify components and take benefit from this such a decomposition. Okay, and we may now formulate the second problem that I consider as a basic, is the branching rules. So by a branching, I understand the kind of similar problem to the previous slide. So if you have a representation of a group, what happens when we restrict it to some subgroup? So even if the initial representation was irreducible, so undecomposable in some sense, if we restrict the set of elements in our among our symmetries, they may break into some irreducible subspaces. Okay, so how to decompose such a restricted representation of a smaller group into irreducible pieces for the smaller group? Okay. For instance, if we have a symmetric group of order 7, okay, so it turns out that it acts in quite, it has several irreducible representations. So I think the largest one, if I'm not mistaken, is of dimension 35. So there's a linear realization of such a group in a vector space of dimension 35. And then what happens when we are dealing only with the effect of the symmetry of the permutation of the 5 elements? So how to pick up representations of the subgroup S5 among a given representation of S7? So it's a combinatorial question, which is so there's an answer, but maybe I don't explain it now. Okay, but if we find such a just as a kind of joke, so we may continue and then see what happens if we can restrict to S3. And so we have such a Shichigo-san decomposition, so just for today, right? But, okay, but I would like to emphasize this procedure for Lie groups, and that was just a small joke. And what I would like to say that the problem of branching of representations is a kind of paradigm that includes many classical problems and questions in mathematics. So in combinatorics, famous Clebsch-Gordon coefficients that describes the way of multiplying symmetric functions. Or Littlewood-Richardson rules for Young diagrams. The Howe correspondence is also another instance of the branching problem. Plancherel formula for symmetric spaces also can be understood and interpreted in terms of branching formalism, fusion rules, etc. So different problems from a priori disconnected areas can be formalized in this way. So this is why I want to show this picture that I like very much, the idea. It's famous citation from Molière play, Bourgeois Gentilhomme, where somebody wants to study good manners, so somebody who became rich, so he wants to study good manners, and he takes some classes and study French language, and then he discovered at the age of 40 that he was speaking prose. He was very, very proud that during all his life he was speaking prose. And so what I want to say is that I think many of us are doing branching problems and branching laws without knowing that. In this sense, it's a kind of paradigm. Okay. So more seriously, so as I said, I will concentrate on particular examples of such problems for reductive Lie groups. And particularly, I will focus on the situation, on the best possible situation where maybe the decomposition is discrete, so the measure is very nice, and irreducible ingredients appear only once, at most once. Okay. And in order to go into this direction, I would like to focus or maybe remind what Professor Kobayashi called the ABC program for analysis of branching laws. So there are different steps, different type of questions arising in this situation. So if we have a given representation, or we have a family of representations, so it depends. So we may wonder about such abstract features as the structure of the branching law. Is it discretely composable? Is it continuously decomposable? So of course it changes completely the situation. The analysis of multiplicity freeness. Such questions are in some sense abstract. Then we may compute, if by chance it happens to work, explicitly such branching laws, explain which pieces will appear and how many times, etc. And then the next stage will be realizing in concrete geometrical models these branching laws through concrete operators that will exchange, intertwine, as we say, different spaces and corresponding actions of corresponding groups involved in this problem. And so today I would like really emphasize this idea of symmetry breaking operators, which progressively appeared maybe in the last, I don't know, maybe 10, 15 years. Okay. So suppose we have a continuous representation of a given group and another continuous representation of a subgroup G prime. So G prime is a subgroup of G. Oh, sorry, opposite direction. Then by symmetry breaking operators, we understand the continuous homomorphisms between the space where the restriction of the representation of a large group act and the space endowed with prescribed representation of a smaller group. Okay? So we consider intertwining operators between two such representation spaces. And so symmetry breaking in the sense that we go from a large group to a smaller one, and holographic operators are elements going in the opposite direction. So they go from a presentation in general of smaller dimension in some inappropriate sense, because in examples that I will give, all these representations will be infinite dimensional. But we may still compare the size. So from smaller object to a larger one, like holography in physics. Okay, so for instance, for unity representations, there's a duality relationship, but in general it may be a little bit more involved. Okay, and what I also would like to emphasize is that when we deal with such a branching problem, then there's a lot of information appearing, and there's whole families of representations of smaller groups that show up, and through symmetry breaking operators we may try to control all this information globally. And one step for that is this notion of symmetry breaking transform, which keeps track of all the whole collection of symmetry breaking operators. Okay, so if we have a representation of a larger group, it can breaks into some collection of representations of a smaller one, and we want to keep the whole information at once. Okay. Okay, maybe few elementary examples. Not maybe elementary is not a good term, but fundamental. Okay. So consider a space of homogeneous polynomials in n variables, and fix the last one, the xn, and then we may rearrange such homogeneous polynomials according to the powers of this fixed, for instance, say a last variable. Okay. So to a given polynomial, we associate a family of polynomials in n minus 1/5 variables, and this operation is exactly a symmetry-breaking transform associated to the pair of groups gln minus 1 with the natural action in space of polynomials, homogeneous polynomials. Okay? So there are one representation of gln and many representations of gln minus 1, and we keep them in a whole family through this procedure. Another very motivating example is the classical theory of Fourier series in one variable. For instance, if we consider the representation of SL2R, so-called spherical principal series, which acts in L2 of R by some multiplier fractional linear representation. Then it turns out that when we restrict it to a subgroup of SL2, which is the group of rotation, then it breaks down into a direct sum with no multiplicities of irreducible representations of SO2, namely the characters. And this decomposition is exactly equivalent to the classical theorem of the decomposability of L2 function, periodic L2 functions into Fourier series. And the fact that it's multiplicity 1 means that coefficients are defined in a unique way, and this is meaningful and consistent theory. Okay, so what is the symmetry breaking in this case? Symmetry breaking in this case is just a way to associate to a given function its nth Fourier coefficient. So it's component in the nth piece of this decomposition, which is exactly the Fourier coefficient. Okay, and as you know, so this procedure is given by some integral transformation, and it turns out that in a specific category, for instance, if we work with holomorphic functions, then such an integral can be understood through the Cauchy formula as so it reduces to some differential operator. And this is a very interesting phenomenon that I will stress on later. In a similar way, we may understand the Fourier transform, usual Fourier transform, as a collection of symmetry breaking operators. The expansion into spherical harmonics, so multivariable analog of the previous example, also can be seen in this way. Okay, so it's not just an ad hoc construction, it's something that formalizes classical expansions in analysis. And if we go into opposite direction, so instead of considering symmetry breaking, we consider holographic transforms. Also, we may connect it with classical things. Consider just the Poisson integral. So to a compactly supported continuous function on R, we can associate a holomorphic holomorphic function in the upper half plane through this transform, and this transformation realizes eigenfunctions of the Laplace-Beltrami operator of the upper half plane, seen as a hyperbolic space, and we have a natural SL2R action both on the upper half plane and on its boundary, which is this real line. Okay. Okay. Then symmetry breaking operators, for instance, for principal series of SL2C, which acts on the space of smooth functions on S2. Once restricted to SL2R, can be decomposed into some representations of SL2R, and symmetry breaking operators in this case are given by integral transformation, this one, which can be understood through its integral kernel. Okay, so the distributional kernel, which is here. And the holographic transformations, the dual map, also can be constructed and understood through this construction explicitly, and it reduces exactly to the classical Poisson transform. Okay. So both constructions of symmetry breaking transform, the collection of symmetry breaking operators, and the opposite direction, the collection of operators going in the opposite direction, in some elementary cases reduce to classical decompositions, the classical expansions. Okay, so what happens if we increase the complexity and consider really non-commutative situation? Okay, so yeah, maybe just I would like to mention two problems. It's very natural. So how to use this transformation? So how can we recover an element of our representation space from symmetry breaking transform if we know it, and if we have supplementary structures of Hilbert structure, for instance, what can we say about norms of Plancherel type theorems, etc. So I will later give some concrete examples and stress on concrete answers to these questions. But let us consider a very prototypical situation where our group is non-abelian, non-compact, so really situation changes. Okay, so the group SL2R acts by a family of series of unitary irreducible representations on the space of holomorphic functions on the upper half plane. There's a discrete infinite family of pairwise non-equivalent unitary representations that we will refer as holomorphic discrete series, and this is the explicit formula for this representation. Okay, and so, for instance, if lambda is a positive integer, then such representations are irreducible and unitary. Very good. But for instance, if we consider a tensor product of two such representations, then and interpret them as a representation of our group, so we restrict it to the diagonal, then such a representation is not irreducible anymore, and it breaks down into a family of irreducible pieces, and it turns out that it's an infinite family, and each piece appears once, but all these ingredients are infinite dimensional representations. So it becomes, in some sense, looks like Fourier series expansion, but in fact it's much more complicated because all these irreducible representations are infinite dimensional. Okay, so this is non-trivial fact, but which is known for a while. What can we say? So this is maybe, this formula is a kind of abstract feature. So this corresponds to the point A in this ABC program that I mentioned before. What can we say explicitly about the operators that will pick up individual pieces in this representation? So analogs of this Fourier coefficients. So how can we find ingredients in the irreducible components? And it turns out that there's an explicit differential operator, bidifferential operator, namely, which will do the job. And it was known for many years. It's the collection of these operators are known as Rankin-Cohen brackets, which were introduced in the theory of automorphic forms, but actually were known much before. And what is interesting is that all these operators are explicit, and they have a very nice internal structure. And the combinatorial coefficients that appear here have a very deep meaning. So the first fact is that such differential operators do intertwine the action of SL2. Okay, so if we modify, so a Rankin-Cohen bracket is a bidifferential operator, so it has two entries and one output. So if we act by SL2 on inputs, then the result or the output also will be transformed by SL2, but accordingly to this branching rule. Okay. So maybe just a few words about this operator. So initially they were introduced by people in modular form theory because it's a machinery to produce modular forms and compute special values of L functions, and also it was used for studying connected problems in number theory, solving Chassis differential equations, etc. There were a lot of activities around Rankin-Cohen brackets in the setting of covariant quantization, because they do define some associative product on the space of modular forms in even formal power series. And they play an interesting role in differential geometry. And maybe I may also mention that analogous problems may be asked for other groups. So I mentioned SL2, but of course we may go beyond SL2 and consider conformal groups, larger conformal groups. SL2 is of course also one of the conformal groups, but it lies on the very bottom. But it works in a more general situation. And if we consider similar problem for holomorphic discrete series of conformal groups SON2 and then restrict to SON-1, 2, then a similar phenomenon holds. We have a good knowledge of the branching, so we have an explicit branching rule, and we have explicit intertwining symmetry breaking operators, which again are very singular in some sense differential operators with a very interesting combinatorial coefficients. And the operators that appears in this general case that we sometimes people call Yule's holomorphic differential operators, they were introduced in the context of conformal geometry for the study of Q curvature, local zeta functions, and scattering operator for local zeta functions, etc. And so also appears in some connections with applications to the physics and anti-de Sitter CFT duality. So there are many things where many situations where these operators play a crucial role. And there are many approaches to the study of these operators. Actually, as sometimes happen, they were known already by classics, maybe a little bit different of shape, but already Gordon and Cayley basically were talking about symmetry breaking operators, but they called for fine dimensional representations of GL2, but basically we can find their roots already in the work of classics. And recently we developed a general method to construct and to analyze symmetry breaking operators. So Toshi Kobayashi proposed these ideas and formalized them as F method, S for Fourier, through the construction that I will briefly recall, and which not only produces symmetry breaking operators, but also explain the structure. Okay, and so I gave a couple of examples where the operators were differential operators. It's a very singular situation, very nice setting, but in general, from probabilistic point of view, all such operators are not differential, but non-local operators. And the interplay between the situations, again, hides a lot of very beautiful mathematics. Okay, but if we want to say something meaningful for the analysis of symmetry breaking operators, we need to fix concrete geometrical models for our representations. And so let us suppose that we have a pair of Lie groups. G prime is a symmetric subgroup of G. Symmetric means that fixed by involution, nothing to do with symmetric, the group of permutation. And we suppose that they act on some manifolds, and manifolds are connected, so in the sense that there exists a smooth map between them. So they connected to each other by a smooth map. And we may also, so we suppose that these manifolds are endowed with homogeneous vector bundles with respect to these groups. And then we may wonder at which condition there exists equivariant differential operator acting between sections sections of these homogeneous vector bundles. So of course we have to explain what does mean differential operator, but it can be done in terms of the support of such maps. There exist some, say, trivial examples. Restriction to submanifold, it's one of the examples. But it turns out that in some nice situations, very symmetric situations, there's a very rich theory of behind and connected, of course, with the representation theory and the branching problem. Okay. And I will give you some examples where we can exactly say where such a space is not empty, and what is the connection with the branching problem. Okay, so as I said, restrictions, normal derivatives can be understood as G-equivariant differential operators. But surprisingly, there are more than this natural geometrical operation. And such as surprising operators can be interpreted in terms of symmetry breaking and concrete realization of branching problems. Okay, so maybe I can formulate one important theorem which says that this problem can be interpreted in an algebraic way. If these manifolds are homogeneous spaces, so we fix, not fix, but there exists some subgroups, say H prime and H, where isotropy of this manifolds. So X is G mod H, Y is G prime mod H prime, and the fibers above these manifolds are finite dimensional, then we may explicitly, not explicitly, but we may understand the space of these equivariant differential operators as a space of intertwiners between some generalized Verma modules. So algebraic objects associated to the action of the corresponding enveloping algebras. So it's a way to reformulate the problem, to change the framework and provide a precise answer afterwards. So this is the first step that we call a duality theorem. Okay. For instance, if G prime is the same group and X and Y is the same manifold, namely the full flag manifold, then this approach was discovered and developed by Constantin in 70s. And the novelty here is that we deal with different groups and different manifolds. Okay. Okay, now, so I would like to show you some concrete examples, and for that I fix a specific setting, and I would like to have not too many such equivariant differential operators, and if the dimension of such a vector space is equals to 1, then there exists only one generator, and it means that it plays a very, very important role. And again, it's using the abstract theory about branching problems, we may figure out the setting, the right setting. Maybe this is what I will do. And then it turns out that if we fix a good category of a good geometrical setting, namely if we consider representations of real reductive Fourier group in holomorphic sections, and if our group is specific types, emission. So here I summarized the nice properties, but if we can realize our group as the group of holomorphic transformation of some emission symmetric space of a specific type, then we have a very nice phenomenon that we call localness theorem, which says that actually all possible intertwining operators that can appear in branching problem are given by differential operators and holomorphic differential operators. Okay, so we can find a very nice, very natural geometrical setting where such a surprising phenomenon happens. Okay. Okay. And actually, it's more, how to say, maybe general phenomena. It turns out, so there's some structure theory which says that we can see this emission symmetric spaces as symmetric domains in some complex vector spaces, and actually also even more precisely we can embed them in some complex flag varieties, and this phenomena propagates upstairs on the level of complex flag varieties, and also we formulated this fact as an extension theorem, which says that any G prime C equivariant holomorphic differential operator, so can be, so maybe I should say in the opposite direction. So the differential operators that I described on the previous slide, differential operators that realize branching rules, comes from some complex objects living on complex flag manifolds. So it's a more general and in some sense more rigid situation. So it doesn't depend on the concrete example. Okay. So what is the idea behind the F method? So very, very roughly, so the idea is to interpret covariance property of differential operators in terms of some constraints on their symbols. And that was performed using the algebraic Fourier transform of the Fermat modules which we saw on the previous slide. Maybe I go very quickly, and it's a little bit technical, so I may skip. Just focus on the main general theorem, which says that equivariant differential operators between sections of two homogeneous vector bundles can be understood as probably vector-valued polynomials invariant or equivariant with respect to some specific action. Okay, so this is the main idea, to translate the equivariance property on the symbol of differential operators. So here, the strange notation dp hat means that we change the picture, we conjugate by some formal Fourier transform, which appears here. Okay, so we identify, we dualize in some sense the Verma module, generalized Verma module with the space of polynomials and translate the action. And finally, what we get some complicated problem on a family of polynomials. So we have to find probably vector-valued polynomials satisfying a system of partial differential equations. Okay, so we are talking about some infinitesimal action of some Lie groups on the space of polynomials. So we want to find solution to some system of partial differential equations. Okay. Okay. So this is the idea, to realize identify differential operators with some polynomials. And so, of course, stated as it is, it's a very complicated, very involved problem, but in a specific, maybe I can give you some positive and explicit results. So when, for instance, we start from line bundle case, so the fibers over the large manifold are of dimension 1, and the pair of groups is also so-called split rank 1, so there's not so many there are not so many, how to say, constraints, I will say in this way. Then we may produce very explicit, very nice answers, and describe explicitly the space of such equivariant differential operators. So the setting that I explained in these 4 points, I fixed using these 4 points, reduces our possibilities to 6 different geometries. So here are, this is the table of inclusions, equivariant embeddings of smaller manifolds into the large one. So there are 6 such geometries that corresponds to the 6 pairs of groups. So the first one is G, the second one is G prime. Okay, and it turns out that we can explicitly describe. So one of the reasons to choose such geometry is that we have multiplicity 1 decompositions. So the space of differential operators is equivariant differential operators is of dimension 1. There are no other symmetry breaking operators than those. So it's really typical situation framework when we can do things in an exhaustive way. And it turns out that there are 2 different families of geometries. In 3 cases, only normal derivatives, so natural equivariant differential operator appear, and in 3 others, very strange operators appear. And in this case, this a priori complicated system of differential equations on symbols just reduces to usual hypergeometric equation. So we are looking for polynomial solutions to the Gauss hypergeometric equation. The most general one is given by the Jacobi polynomial. And for instance, now we can give explicit responses, and it turns out that if we consider the branching problem for holomorphic discrete series of this group, un1 times un1 restricted to un1, so it corresponds to the equivariant embedding of n-dimensional projective space in a two copies of n-dimensional projective spaces, then there exists up to a constant only one possible equivariant differential operator, and this operator is its symbol actually is the Jacobi polynomial. So this is what says this formula. And if we consider the case when n equals to 1, so u1 times u1 restricted to u11, so then this is exactly what we started with. So I just formulated this problem for SL2R, but which is conjugate in SL2C to u11. It's a different real form. But as the extension theorem says, it doesn't really depend on the choice of the real form. Then this formula reduces exactly to Rankin-Cohen operators. So Rankin-Cohen operators are, the symbols are Jacobi polynomials. And this is why it happens. And similar phenomena happens for order geometries, for symplectic groups or for embeddings of Lagrangian Grassmannians. So in this case, the symbol is Gegenbauer polynomial, which is Jacobi with same parameters. So again, the same scheme works. And in the conformal case, again, the same phenomenon happens. And again, such operators are explicitly given by orthogonal polynomials, classical orthogonal polynomials. And this operator is exactly that the operator we started with, namely this Yule operator. Okay. Okay, so I have not so much time, but maybe just a few words that maybe I would like to, a little bit maybe technical theorem, but from my point of view, very interesting because it shows the power of this approach. So it's very important to understand the structure of multiplicities appearing in the branching problems. This analysis of symmetry breaking operators, even for SL2 case, allowed us to predict some phenomena of blowing up of multiplicities. And that was performed using the structure of polynomial solutions to the hypergeometric equation. It turns out that there exist some parameters where very singular cases where there exist two linearly independent polynomial solutions to the Gauss hypergeometric equation. So, by the general theory, such operators do provide intertwining operators. So we can predict multiplicities, so go in an opposite direction, not start from nice case and see what kind of operators may occur, but knowing operators, we can predict multiplicities. And in SL2 case, everything can be done really by hand, and we can construct operators and show that such a nice phenomenon, not nice, interesting and curious phenomena appear. Okay, so I have maybe few minutes. So maybe just last remark. So this phenomena relies on a Kuhn connection formula for hypergeometric functions. So it's very classical complex analysis in the 19th century that plays such a non-trivial role in understanding of representation theory of SL2. So again, so it's a very nice interplay between different fields. So maybe that I may skip. Maybe just say a few words about this correspondence that the F method provides. So there's a connection between symmetry breaking operators and some special orthogonal polynomials. The examples I gave was very low dimensional ones, but it works in general. At least there's kind of philosophy that says that it works in general. There's some series of undergoing work, for instance, by Nakahama, where there are connections with multivariate orthogonal polynomials associated with root systems appear. So there is such a correspondence. Intertwining properties, algebraic property, corresponds to some differential equations. In lower round case, hypergeometric differential equations. In general, much more complicated hierarchy of specific ordinary differential equations. The symmetry breaking transform also play a role. So the collection of the symmetry breaking operators keep track of the L2 norm of orthogonal polynomials. The branching law can be understood as a kind of L2 completeness of these orthogonal polynomials in appropriate space. And if we go in the opposite direction, so also we have similar phenomena for holographic transform. And in the last few minutes, I would like to just mention some. So this is what I said. So we can increase the number of variables with the rank, the dimension, etc. So the examples I provided were the first ones, but of course we can expand the complexity, but there's some structure in this complexity. So it goes in a very nice way. And maybe just a few words about this general idea of keeping track of the whole collection of symmetry breaking operators. So if we have a family of linear operators between spaces of functions somewhere on some sets x and y, then we may construct a kind of formal power series associated to this collection. So if, for instance, the set x is just one point, then this construction reduces to the usual notion of a generating function. If these two sets are the same, then we have some extra structure. We have a ring structure on the space of endomorphisms of functions on this set. So we can compose such operators and not define, but just include the notion of the semi-group of operators, the exponential of a given operator into this construction. And so this is how it works, for instance, for classical semi-groups or for, so if we have some specific differential operator, we can iterate it, construct the whole family of powers, and see what is the generating function. So then it gives rise to specific semi-groups that play a very important role in PDEs, in harmonic analysis, etc. And a very naive question: what happens if we apply this idea to a more involved family of operators, namely which are not powers of some specific differential operator anymore, or some specific operator, just not necessarily differential. And for instance, what happens if we construct or consider a generating function or generating operator for this Rankin-Cohen brackets? So here I consider the case where there's no more spectral parameters. So this is just, So let us consider such a family of bidifferential operators on the space of holomorphic functions in two variables. Okay? So what happens if we just formally consider the generating function associated to it? And then it turns out that we may say we may compactify all the information in one specific operator, which is this one. So it's not a differential operator anymore. It's some integral transform, complex integral transform, which consists in integrating along two cycles in C2 a given function with respect to some specific kernel, kind of, cannot say Cauchy kernel, but it's inspired, say, in some sense by Cauchy kernel. And so it turns out that such an operator is well defined. And so let me just remind that the operators I mentioned on the previous slide are just particular cases of Rankin-Cohen brackets that we discussed at the beginning, with L prime and L second just equal to 1. So the simplest situation. And then it turns out that this integral transformation given by some explicit formula that I mentioned plays exactly the role of the generating operator for this family of symmetry breaking operators that we called Rankin-Cohen brackets. Okay, and this formula is not formal. So the dependence on T is analytic. So it's a genuine formula in some sense, not formal formula, not a formal power series. This is what I would say. And there are many. It's not just a curiosity, but there are many motivations for considering such operators, because actually many very nice, geometrically nice differential operators can be understood as residues of some meromorphic families of equivariant transformations, non-local integral transformations. For instance, Dirac operator and its iterated powers can be seen as residues of some meromorphic families of intertwining operators. Rankin-Cohen brackets also can be seen in this way. But so if you want to consider residues, we have to know these meromorphic families. And in this situation, motivation was opposite. So how to find meromorphic families of some symmetry breaking, or not some meromorphic families of equivariant operators, non-local equivariant operators with prescribed residues in prescribed poles. And this is this generating operator is the key ingredient of this construction. So this is the tool to, if I can say in this way, provide a kind of non-commutative Mittag-Leffler theorem for a family of symmetry breaking differential operators. Maybe, so the time is over, so maybe I stop here.